Today we're going to talk about fluid dynamics, which is the physics of fluids and motion. In this we'll be talking about flow rate, Bernoulli's equation, and the concepts of viscosity, diffusion, and osmosis. About half of this lecture is not problem-based, so the quiz on this lecture will have probably some fill-in-the-blank or matching or something like that in addition to problems to solve. Now this is the way in which you need to look at fluids flowing through a pipe, most pipes being circular, but it's a circular pipe. And in this situation, the flow rate is the volume of fluid that passes by any particular point, and here it's labeled P, through an area at that point during a specified time. So flow rate is given in terms of volume per unit time. And volume can be something like liters or milliliters, but needs to be transferred into something like cubic centimeters or cubic meters, because many of the other concepts we'll be looking at are in meters per second or square meters, etc. Now the velocity is equal to this distance traveled over time, as we well know. And again, Q, or flow rate, is equal to V over T, and V is this cross-section of volume right here, which would be D times the cross-sectional area over T. So if you substitute this for this, you end up with Q is equal to V, the area, times the flow rate, or times the velocity, excuse me. And that is what we have right down here. This is an important equation that you need to keep in your lexicon of equations. That is, flow rate is equal to volume over time past a particular point, which is equal to the area times that distance divided by time, which is equal to area times velocity. And we'll be using this equation to solve some problems here in just a second. Now, when a pipe changes cross-sectional area, then what happens is that the area gets, if the area gets smaller, then this distance, D, has to get larger. And in order for that to happen, the velocity has to increase. So when a tube narrows, the same volume has to occupy a greater length. For the same volume to pass point 1 and point 2 in a given time, the speed has to be greater, or the velocity has to be greater at point 2. The process obviously is reversible. If you're traveling from a narrower tube to a larger tube, then the velocity has to slow down. That's because the flow rate remains the same. So if the area gets smaller, the velocity has to increase. If the area gets larger, then the velocity has to decrease. So since the flow rates are the same, Q1 is equal to Q2, then A1 times V1 has to equal A2 times V2. And this is another equation that you should put in your lexicon of equations. So let's take a look at a couple problems using these concepts. Blood is pumped into the aorta at a flow rate of 5 liters per minute. If the radius of the aortic valve, that's the valve that leads out of the left ventricle and into the aorta, is 1 centimeter, what is the velocity of blood through the aortic valve? Okay, so let's take a look at how we would do this problem. First of all, Q, flow rate, is equal to 5.000 liters per minute. Now we have to change that, and 1 liter is equal to 0.001 meters cubed. And I just looked that up in a book, and 1 minute is equal to 60 seconds. So if you do the math here, then Q converted to a cubic meters per second comes out to be 8.333 times 10 to the minus 5 cubic meters per second. And we have to also convert the 1 centimeter is going to be 0.01 meters. So the area, which is pi r squared, is going to be pi times this squared, or 3.142 times 10 to the minus 4 square meters. Now we're ready to move forward with the problem. Q is equal to AV, and so V is going to equal to Q divided by A, which is equal to 8.333 times 10 to the minus 5 divided by 3.142 times 10 to the minus 4. And we get 0.2652 meters per second for the velocity of the flow. So that's the first problem. Now the second problem here says that an individual has an aortic valve disease, and so the opening narrows and it causes an increase in velocity across the valve with the flow rate remaining the same. If the velocity doubles, what's the new radius? So if the velocity increases by twofold, then that means that the new velocity is equal to 0.5304 meters per second, and we know Q is equal to A times V, so that means that A now is equal to Q over V, and so that's going to be 8.333 times 10 to the minus 5 divided by 0.5304. So A is going to equal 1.57 times 10 to the minus 4 meters squared, which obviously is going to equal pi r squared. So R is going to equal 1.57 times 10 to the minus 4 divided by pi, and take the square root of that. If you do the math here, you get 7.071 times 10 to the minus 3 meters, or 0.7071 centimeters. So a decrease from 1 centimeter to this, so less than a 50% decrease in radius, causes an increase in velocity of double velocity. Now I can tell you that this is actually how they measure the amount of stenosis that has occurred in a valve, is they can use a Doppler ultrasound to measure this change in velocity, because if you fire a sound wave off of blood, it acts like sonar, and the faster the blood is traveling, the different sound waves you'll hear, and you can calculate this velocity change and then use this formula to calculate the change in the diameter or the radius of the valve. And that's actually how. Now let's move on to Bernoulli's equation. Bernoulli's equation is a way of relating pressure and velocity of objects moving, of fluids flowing around and amongst various objects. Bernoulli's equation states that for a compressible, incompressible, frictionless fluid, so a somewhat idealized state, because we know that there's no such thing as frictionless, and we know that there's no such thing as incompressible. However, for high school physics classes, we can assume both incompressibility and a lack of friction. The following relationship is a constant. That is to say that this pressure plus 1/2 the viscosity of the fluid times its velocity squared plus, again, its density. I'm sorry, I said viscosity. It's density times gravity times height. So if you add these three factors up, so it's pressure plus its kinetic energy, so to speak, plus its potential energy, so to speak, you end up with a constant. And where Bernoulli's equation is very useful is the fact that if you have an initial state of parameters, because it's a constant, then the second state has to be equal to the first state. And you can use this to calculate when there are changes in the environment that change the flow across or around various objects. And this is the important equation in Bernoulli's equation. So for example, you have several states here that occur and cause various different things to happen. In every case, this equation is active. Now, many times, like for example, here you have natural gas flowing, and because it flows at a certain velocity, it starts at one velocity, flows at another velocity, and then out here, the pressure and velocity are different. And because of that, this pressure out here is less than this pressure in here, and it draws air into this situation. Similarly, when a perfume bottle, you're pushing air across an open situation, and again, the pressure here is less than the pressure in here, and that draws the perfume out and leads it to come out. Each one of these is similar situations to that. So if the velocity at point 1 is greater than the velocity at point 2, then the pressure at point 1 will be less than the pressure at point 2, because these other factors such as height and density are not changed. So you see the relationship here is if the sum of this and this are equal to the sum of this and this, if you increase this or this, then this ends up being decreased. So for example, looking at this, if this is V1 in here and this is V2 out here, then the pressure out here has to be less than the pressure in here, or vice versa. And so that's what leads to the flow of air in these various situations. Flow is always from high pressure to low pressure, so by inducing these changes in velocity, what you do is cause a pressure gradient, which gives you the desired flow. Now this is a situation where Bernoulli's equation is used to achieve a certain effect. It can explain how we get lift. So for example, if the velocity, because this flow is the same as this flow, the velocity here must be greater than the velocity under the wing. If the velocity over the wing is greater than the velocity under the wing, then the pressure here is greater than the pressure here, and you get lift. And it's also used in sails. So what they're saying here is the velocity over the top of the wing is greater than the velocity over the bottom, under the bottom of the wing, and therefore the pressure here is less than the pressure here, and so you get lift. Similarly, if the flow rate is on the bottom here, if the velocity is greater on the bottom than on the top, then the pressure will be greater on the top than on the bottom, and vice versa. And so you use that to either cause motion in this direction or motion in this direction. So for example, the velocity in the front here is greater than the velocity of the back here, and therefore the pressure in the back is greater than the pressure in the front, and this leads to a motion in this direction.